Brick architecture carries centuries of history in its texture. These ornate facades and plaster accents suggest a sense of permanence, a feeling that these walls are as solid as the ground they stand on. But that stability is often an illusion. When a seismic wave hits, the rigid connection between the bricks dissolves, turning a family home into a massive pile of rubble in a matter of seconds. This is the reality of unreinforced brick masonry. It remains one of the most common construction methods on the planet because the materials are cheap, local, and require very little specialized equipment to assemble. The problem is that these walls are incredibly brittle. They are designed to hold weight sitting still, but they have almost no capacity to bend or absorb the dynamic energy of an earthquake. In developing regions or across the steep slopes of the Himalayas, expensive retrofitting with steel or reinforced concrete simply isn't an option. Builders have to work with the bricks they have. To protect these communities, researchers are looking for a zero-cost solution, a way to make standard bricks exponentially stronger using nothing but the geometry of how they are stacked. Every brick wall relies on a bond, a specific structural logic that determines how forces travel through the masonry. Two patterns are central to this study, the English and Sussex brick bonds. The English bond uses an alternating alignment of headers and stretchers. In contrast, the Sussex bond uses an elongated pattern, ensuring vertical mortar joints are constantly interrupted. Simply rearranging the bricks into these different configurations dictates how the entire building responds when it is pushed to the point of collapse. In the lab, researchers introduced a second variable to the test, comparing traditional burnt clay bricks against a modern alternative, fly ash. Fly ash bricks are made from the industrial byproduct of coal power plants. They are sustainable and cost-effective, but their smoother surfaces often struggle to bond with standard mortar. To measure their strength, engineers used a universal testing machine to apply massive vertical pressure, simulating the gravity-induced stress of a multi-story building. As the pressure climbs, the structural differences become visible. The English bond specimens begin to yield and crack under the load, while the Sussex bond walls continue to hold the weight. This lab observation suggests that geometry alone can upgrade a wall's load-bearing limit, even before a single piece of steel is added to the design. But why does the Sussex pattern hold up so much better under a crushing force? To see what's happening inside the masonry, engineers use ANSYS computer models to map the invisible paths of stress. In the English bond, the stress localizes quickly. Because the joints are aligned, the pressure can drive a crack straight down the center of the wall. The Sussex pattern forces that energy to redistribute. Because the bricks are heavily overlapped, a crack cannot travel in a straight line. It's forced into a long, jagged, zigzagging path that dissipates the force as it goes. This geometry acts as a built-in shock absorber, spreading destructive energy through the entire wall rather than letting it concentrate in a single point. But earthquakes don't just push down. They generate lateral forces that push walls sideways, often causing them to buckle outward. This is a 3-point flexural bending test. It's designed to measure how much a wall can bow before it snaps. This strength depends entirely on the interfacial bond, essentially the grip between the brick surface and the mortar. Rough clay bricks have a natural advantage here, as the mortar can seep into their pores. The smoother fly ash bricks separate from the mortar much more easily. However, when no smooth fly ash bricks are stacked in a Sussex bond, the failure mode changes. Instead of a sudden, brittle break, the masonry begins to bow and stretch, absorbing the energy. This is ductility, the ability to deform without collapsing. A wall that bows gives the people inside a warning and, more importantly, time to get out before the structure fails. The final data reveals a clear hierarchy. For compressive strength, clay bricks in a Sussex bond are top performers. More significantly, flexural tests show this efficient bond allows sustainable fly ash bricks to achieve the highest bending resistance of any tested combination. This means builders in seismic zones can safely use cheaper, eco-friendly industrial waste to build homes, provided they use the correct geometry. The survival as a home in an earthquake zone depends less on the raw strength of a single brick, and more on the intentional path the mason creates for energy to follow. By optimizing the internal geometry of these walls, we can build a zero-cost blueprint for resilience into the very foundations of the regions that need it most.